So we're going back to limits today. If we recall, what's the first thing that we were supposed to do anytime we are trying to evaluate a limit?
Plug it in.
First step is just plug it in. And when you plug in the value into your limit, you either get some number and you're done, or you get something like 8/0, which doesn't exist. So you say it doesn't exist and you're done. Or you get something like 0/0. And what is 0/0?
Indeterminate.
That's our indeterminate form, right? And that's when most of our limits had more work to be done with them, right? We either had to factor or we had to do something like multiply by the conjugate, or sometimes we did a U substitution. Sometimes we ended up using the sandwich theorem or some other tricks to simplify things down with trig functions, all kinds of different stuff, but it required extra work. And so we're going to look at one other thing that we can do when we get a limit that is indeterminate. And it's called using L'Hopital's rule. And so it's got two forms to it. This is the first form that we're going to talk about here, is that if we end up with an indeterminate limit, so if we have the limit as x approaches a of f/g, a rational function, or it doesn't have to be a rational function, but a quotient of two functions, and it comes out to be 0/0, if we want to, we can take the derivative of the numerator and the derivative of the denominator and evaluate those at a, at this value that we were approaching for our limit. And this result is equal to the limit of the original function. Okay? So let's take a quick look at how we might do this. If that sounds easy to you, hopefully that sounds easy to you, that's because it is, for the most part, fairly easy. Suppose I asked you for the limit as x approached 3 of x squared minus 3x over x squared minus, how about minus 8x plus 15. This is a limit. So what's the very first thing we should do to our limit?
Plug in 3.
Plug in
3.
three.
If we plug in 3, what do we get? Numerator is 0, right? What about
0/0?
Looks like the denominator is 0. We get 0/0. So we can use L'Hopital's rule, and anytime you use L'Hopital's rule, they want you to indicate on the AP test that that's what you're using. So we can say that using L'Hopital's rule, this should be equal to the derivative of the numerator, which is what? 2x minus 3 divided by the derivative of the denominator, which is 2x minus 8, evaluated at x equals 3. This is what L'Hopital's rule says we can do. Take the derivative of the numerator, take the derivative of the denominator, and then make a new quotient and evaluate them at your original a value. Okay. Note that we did not take the derivative of this using the quotient rule. It's the derivative of the numerator divided by the derivative of the denominator. We're not actually finding the derivative of this function. We are treating it as if it was two separate functions and finding the derivative of each. And so what does that give us? It gives us 6 minus 3 over 6 minus 8, or what? Negative 3/2. Yeah or no?
Yeah, that's how you do like subtraction.
That is how you do subtraction, yeah. And we'll note that had we done this the old way, we could have factored, right? It had x times x minus 3 and x minus 3 times x minus 5 down here. And then if we plug this in, we now have 3 over negative 2, which is the same. So it should come out to be exactly the same every time. Easy enough?
Yeah.
Sometimes this might be easier, sometimes this might be easier. I think taking the derivative is most of the time quite a bit easier than trying to factor this stuff out. So let's see if we can look at these two problems here. Before we use L'Hopital's rule, what's the first thing we should do?
Plug it in.
Plug it in. Plug in 2, what does that give us here?
0 over 0.
0.
0 over 0, indeterminate. So we should make this now a limit as x approaches 2. And we're going to say using L'Hopital's rule, and you'll write it all the way out because they want you to write it all the way out, but I'm lazy and not taking the AP test, so I'm not going to. I'm just going to write LH. What's the derivative of the numerator?
(2x).
And the derivative of the denominator?
1.
And so if I evaluate that at 2, what do we get? We get 4. And there's our limit without any factoring needed. What about the second one there? Plug in 0, right? Gives us 1 minus 1 over 0. So definitely indeterminate. So this should be the derivative of the numerator. What's the derivative of root 1 plus x? The derivative of root 1 plus x should be 1 over 2 root 1 plus x times the derivative of 1 plus x, which is 1. And then the minus 1 is 0, all over 1. And we're going to evaluate it at x equals 0, which ought to give us 1/2. Good or no?
Good.
It's concerning to me that when I ask what's the derivative of root 1 plus x, nobody tells me that this is what its derivative is. Hopefully you can all do that. Okay. So note that on this one, I wrote it out as this equals the limit as x approaches 2 of this new derivative over derivative, whereas here I just wrote the evaluated at. Both of these are acceptable. And so if we think about doing it this way, where our first limit equals the limit of the derivative of the top over the derivative of the bottom, what would happen, do you think, if when we took our first derivative of each of those got 0 over 0 again?
Did you take the second derivative?
Yeah, we could just take another derivative and reapply the rule. Exactly. And what do you think would happen if I did it a second time and got 0 over 0?
You just keep going until you don't get a indeterminate.
Exactly. You can just keep going and do it as many times as you need to until the result that you get is no longer indeterminate. So this means that if we get 0 over 0 multiple times, you can use L'Hopital's rule as many times as needed. I know how to write. As many times as needed until it is no longer indeterminate. As soon as it becomes indeterminate, you cannot use L'Hopital's rule. So if I give you a limit to find and it's not indeterminate to start with, don't just try to use L'Hopital's rule. You'll get the wrong answer. This only works when it is indeterminate. Good. So you always have to check and plug in the original number and make sure it's indeterminate before you go and use the rule. Good or no?
Good.
All right. So let's take a look at this one. What should we do first?
Plug it in.
Plug in 0.
which gives us square root of 1, which is 1, minus 1 minus 0 over 0 squared. So definitely 0 over 0, right? So using L'Hopital's rule, we should get the limit as x approaches 0. What's the derivative of the denominator?
2x.
2x. What's the derivative of root 1 plus x? It's 1/2 of 1 plus x to the negative 1/2, if we want to write it this way. And then minus 1 becomes 0, and minus x over 2's derivative is just minus 1/2, right? Minus 1/2 x is the derivative. Get rid of the x. And what should we do? We should plug into 0, and what do we get if we plug in the 0? What's 1 to the negative 1/2? Now 1 to any power is 1, right? So we've got 1/2 minus 1/2, 0 over 0. So what should we do? Use L'Hopital's again. Now our derivative in the numerator becomes negative 1/4, 1 plus x to the negative 3/2. And the minus 1/2 is a constant, it goes away. And then we have a 2 in the denominator. And as soon as we just have a 2 in the denominator, we can probably see that we're no longer going to get a 0 down there. So when I plug this in, I've got negative 1/4 times 1 to the negative 3/2 all over 2. 1 to the negative 3/2 is still 1. And we get negative 1/8. Good or no?
Good. Good.
Wonderful. So we can reapply this as many times as needed. All right. Do you remember there was an indeterminate one that I told you we needed to memorize what its value was, and we had to prove it first, and it took us like 15 or 20 minutes because I drew like a circle with like a triangle and a sector of a circle and another triangle, and we had to use the sandwich theorem and find a bunch of areas and relate together the functions and then do a bunch of algebra to finally get an answer. Remember that? You guys remember doing that?
Isn't that the trig limits or something?
Yeah, I was within the trig limits, right? It was this one. The limit as x approaches 0, sine x over x, right? What does this equal? It equals 1, right? I told you a long time ago, you got to memorize this one so that you can apply it to other limits. So this should be 1. We know it's 0 over 0. L'Hopital's rule makes this much, much easier. Using L'Hopital's rule, derivative of sine is cosine, derivative of x is 1. This just becomes cosine of 0. Cosine of 0 is 1. Takes a little bit less time than doing it the other way, doesn't it? Just a bit less. Good or no?
Good.
All right, wonderful. Let's talk about a new indeterminate form. I mean, sort of new. It's not really new, just new to you. Infinity over infinity. So infinity over infinity is another indeterminate form, and you can also use L'Hopital's rule for it. So let's first just take a look at why this is infinity over infinity. What is secant? Secant is 1 over cosine, right? And tangent is sine over cosine. So if I plug in pi over 2 to this, what's the cosine of pi over 2?
0.
Yeah, 0 over 1 plus sine of pi over 2 is 1, and cosine of pi over 2 is still 0. And so really, though, we're not actually getting to 0 here because we're just getting very close to pi over 2, which means that this number, this 0, is really just a very, 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 very small decimal. And so if I take 1 and divide it by a very, 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 very small decimal, we get infinity, don't we? And same here, 1 plus infinity. Well, 1 plus infinity is just infinity. And so we can say that this is indeterminate of the form infinity over infinity. And so we will use L'Hopital's rule to rewrite this as the limit as x approaches pi over 2 of, what's the derivative of secant x?
Secant x tan of x.
Secant x tan x. And the derivative of 1 is 0, so that goes away. And the derivative of tangent ought to be secant squared. Yeah? Which I think we would probably all agree that it would be nice to rewrite this as just tangent x over secant x. Might as well simplify it, right? And what does that equal? Tangent of pi over 2, just like before, is infinity, right? And secant of pi over 2, just like before, is also infinity. So what do you think we need to do?
Take the second derivative.
All right, we could take a second derivative. So if we use L'Hopital's rule again, we're going to get the limit as x approaches pi over 2 of derivative of tangent is secant squared. Derivative of secant is secant tangent, which is just secant over tangent, which is infinity over infinity. True?
True.
Yeah, so what should we do? Should we just take another derivative, top and bottom again?
No.
Okay, sure,
because-
let's do that. What's the derivative of secant?
It would just give the same thing as before, right? Secant x tan of x over secant squared x.
Yeah, we're just going to get this, which is just going to put us in sort of an infinite little loop here. So maybe this wasn't the right thing to do it again. I know we got infinity over infinity, so we could try it, but what else could I do with this? Couldn't I just rewrite this? Yeah, as sine over cosine over 1 over cosine, which is just a limit as x approaches pi over 2 of sine x, right? If we simplify that out. And the sine of pi over 2 is 1. So if you end up getting yourself in an infinite little loop, particularly with trig functions, but with any other functions, it means you need to do some simplification of your function first. So find a way to simplify your function. Good or no?
Good.
Wonderful. All right, let's do one more here. Then we'll do a couple more after that, after we talk about this one. So first thing is we should talk about what happens as natural log goes to infinity. What happens to the natural log function as it goes towards infinity?
Doesn't that also approach infinity?
It does approach infinity. And what about the function 2 times the square root of x?
Also infinity.
Also goes towards infinity. Yep. So we got infinity over infinity, which means we can apply L'Hopital's rule. The derivative of natural log of x is 1 over x, and the derivative of 2 root x is 2 times the derivative of root x, which is 1 over 2 root x. So cancel the 2's. Right, and we've got 1 over root x and 1 over x above it. Which, let's simplify. We learned from the last one that we should always simplify if we can. Root x over x which is x to the half over x to the first, or just 1 over root x. And as x goes towards infinity, the square root of x goes towards infinity, and 1 over infinity should be
approaching 0.
good or no? Good or no? Everyone okay with that?
Yep.
All right. Let's do this. The limit as x approaches infinity of e to the x over x squared. That ought to be infinity over infinity, right? So using L'Hopital's rule, this should be the limit as x approaches infinity of what's the derivative of e to the x?
E to the x.
Okay. And the derivative of x squared is 2x, which is still infinity over infinity, isn't it? So let's use L'Hopital's rule again. This becomes the limit as x approaches infinity of derivative of e to the x is still e to the x, derivative of 2x is 2. As x goes towards infinity, this is infinity, or this limit doesn't exist. Okay. Which of these things increases more rapidly, e to the x or x squared?
E to the x.
E to the x does, right? And the numerator increased more rapidly than the denominator. We got infinity. Which of these increases more quickly, natural log or square root? The square root increases more quickly than the natural log function. And that's why this goes to 0. The denominator gets bigger faster than the numerator. So the denominator is always bigger than the numerator. And that's going to tend towards 0. So if the numerator increases more quickly than the denominator, it's infinity. If the denominator increases more quickly than the numerator, it's 0. So it might help us to sort of order how fast things increase. The slowest is logarithmic. Faster than that is root functions. Faster than that is polynomial functions. And faster than that is exponential functions. And what's faster than exponential functions? Nobody knows? Factorial functions, but you don't need to worry about those. All right, so if I asked you what's the limit as x approaches infinity of x to the 100th power over 2 to the x, which one of those increases more quickly?
The denominator.
The denominator does over time as we go towards infinity. And if the denominator is getting bigger faster than the numerator, we should be going towards 0. But if I had that flipped around, 2 to the x over x to the 100, that should be infinity. Good or
Do
no?
you need to show work for a problem like that?
Nope, if you just did this, that'd be good enough for me. Any other questions on that?